All right, here's what they don't understand about light. It doesn't flap like a wave like that, and they come here and go this way and that way through a double slit experiment. No, this is a single slit. And light spins like this. That's the particle. It has a magnetic field. And it spins like this as it goes forward. And they're all over the place. There's a zillion of them coming this way. Some of them are way over here, some of them over here, some of them over here. But they have to funnel down through that venturi, and then they spread back out again. Well, they funnel down, and you get a white shot in the center. And then they push each other out very, very evenly. As you can see, you see how even those interference patterns are? They call them interference patterns. Well, it's not interference patterns. They're spinning this way, and every one of those particles has a field on it that pushes the next particle on it, the next to it out here. Stay away that far, you stay away that far. And they're just nice and evenly spaced. There must be an exact charge on these particles to make this kind of a separation. And you can see it's just nothing more than a drill bit. It's coming in this way and smacking in hard here as it hits. So I would say it's spinning this way, and it goes down and under, and then smacks this side. So you see it here, and then it goes down and under. It's like a drill bit. And that's what it looked like. Now, red is way long out like this. Green is about like this, and blue is way down here. And I'll show you the differences. So red is slow, or its wavelength is just longer. They say all light goes the same speed. I'm not sure that's true. I think red does not go as fast as green, and blue goes even faster. But when you see all three of them together as white light, it's just basically one speed. Could be. I don't know. I'd like to see them measure the speed of light a bunch of different ways now, because it's just not right. We can speed up light. That's no problem at all. You see that? And we can split the particles of light, which I just showed you what light is right here. This, and Fermilab agrees with this. Where is the Fermilab one? Right here. These are the Fermilab particles. The black one with a fuzzy edge around it. The glowy one that can get big and it can get small. The black one, forget those two. I don't know why you put those in. This is just, it never gets smaller, never gets bigger. It's one size fits all, and that's the dark matter. That has all the weight, and I can prove too. I can prove everything I'm saying. This one is the energy source. Now, here it is right here. There they are. There's the black one with the glowy edge around it. That's the other black one with the glowy edge. Here is just the black and white of this. This shows it with its energy values. Now, what are we seeing here? We're seeing the leading, it's going this way. You see these little white particles? Those are what this is banging into, and this is getting energetic, because anytime you bang something into something else, it takes on energy. It gets hotter and a good strong field about it. And it's pushing these out of the way, get out of the way. This one here is hiding behind the black thing. It's like, no problem with that one, because the black doesn't interact with anything. The white ones want to be attached to the black, yes, but the black, it's a different animal. And here it is right here. Here's the black and whites after they break apart right here at the venturi. And there's the black particles. They're all around trying to get back into the white. Because that's all we did start with was light. We didn't start with these big, huge chunks, big, gigantic jobbers like that. We started with little bitty parts like this. All right, so they come right back together. You see, from here to here, I don't know, it's not much of a distance. And from here to here, they're already almost back together. And they come back together because the black seeks the white. That's why the distance that they're trying to calculate how far out before these quarks add back together again and become whatever they become. Well, it depends what they're hitting into, first of all, but secondly, all they're going to do is glue back together with something. And there's going to be light. Now, that light might still burn you for a ways out here. It might be strong enough to burn you. because you still got some high energy particles, but as they concuss more and more with the atmosphere, they just slow down, and eventually they'll turn red, and eventually they'll just stop. So there is no particles that there's no speed of light. First of all, you can speed it up, no question whatsoever. You can slow it down, no question whatsoever. Here's blue coming in hot. And why do I go? Because here you can't even tell there's two particles. It's a dipole, two dipoles together. It's the photon. By the time you get out to here, you can see it. So the spin is spinning to the right, which means the glow would drift to the left, which it is. And now we can see there's two. That's no question it's slowing down. Absolutely no. Zero. All right, and this is no question that's speeding up. Another zero. And this is just what light looks like when it's just getting ready to accelerate. Otherwise, you wouldn't even see this. You would not even see that. Light would just go through the air unseen until it really starts to accelerate, like with this red laser. Well, when I say, yeah, it's accelerating there. You might see it in the air, I don't know. Here's another one from CERN. There's their Higgs fields. It's the same stuff we're seeing. You see, did I show you the Higgs fields yet? I don't know if I did. But here's the entangled particles, just to be sure I don't miss anything. Like I said, I got interrupted a few times. They're coming through the Venturi, and they're starting to try to find their own way in life. And they're pushing each other out of the way, and they're sort of intertwined and interweaved. And you see them, anytime you see more glow, it's more energy. That's as simple as that. And here and there, you're going to get more energetic little bundles that they have impacted more. And this one here is squeezing over and cutting in on somebody. And those really will be the Higgs fields, which are these. Now, these Higgs fields are coming at us through the Venturi. The Venturi's back here. That tiny little spit. And the white particles are coming through. And all of a sudden, they turn into these circular little disky fields. So the white is recombining with the black, and that is what a Higgs field is, when the white comes back to the black, not the other way around, where the Higgs field just drops off and the white and black just go on their way. No, absolutely not. They say they decay and give off the particles. No, that's when they smash their particles, it's when they come back together, they see the Higgs. And here it is right here. This is coming out at us. So the Venturi is here. The light comes through the Venturi, just the white. And right in this area, there's nothing. There's nothing but white. Nothing but white. And then you see these little strips here. See that? And it hits the black particles. It looks to me like they hit the black particles and they start spinning. And they all come out swishing all over the place. And here I'll show you that a little closer up from the side. Here it is right here. What we were looking at is into here. So we're seeing the black ones start to form around here. And we're looking into the whiteness of that. You see? We're just looking into the whiteness, and these are starting to try to cuddle in to get to the black. The white ones will get to the black together, and then they just start spinning off. Now here's one on steroids. Now don't forget, this is real stuff. This is not like the stuff you're seeing from CERN. This has actually happened. That right there is the white coming through the Venturi. Now you can see there's a couple little tiny black ones can squeak through every now and then, but most of them don't get through. And they might be just jumping in right here. I don't know. But look at this one here. You see this? They're just splashed into whatever medium is here, and it's just the atmosphere. And it's right in Rod's workshop where he did this, where he experiments. Now, all of these fields just show up instantaneously. And the little black particles you see coming up here, You see in the black and black and black and black. This is starting to mold itself into a field. That's what I'm seeing. Could be wrong. But they all seem to be getting bashed with these little white particles. And where they hit the white, they just start to spin into these fields. These are the Higgs fields. I don't think anybody could deny that. All right, this is what they show for simulated, but they don't ever see them. They just see debris. That's the problem. They don't see like we see. We see the actual particles themselves. And they do too, but they just see them in a ball of debris. What haven't I shown you? These are the two speeds. I think I showed you that. Same particles. The green and the blue and the red are all the same. And it's coming through, just pushing the red out of the way. And then reconcussing out here because it's got much more energy. Much more energy, that's all I can say. And here's the particle itself. Same identical particle as the red. Has a little spike coming up in the top and the bottom, and that's it. And they're always oriented towards Earth. These are the neutrino values before they hit photon. And here's the red. Let's see, where are you here? This is the red. Excuse me. These are the neutrinos before they have the full energy of a photon. Now they have a full photon. Now the only reason we're seeing them here is because they're stacking up on themselves. You see out here, you don't see the photons out here or down here. You don't even see anything over here. But because these are directly in line and stacking up against themselves, as it pushes back, all of a sudden they think they hit a wall. That's why you see the photon here. You see it over here, it's just starting to be turned into a photon just directly in line with the Venturi here. The other ones, they're taking on some kind of neutrino values up here, which means they're concussing enough where they're changing flavors. This one changed from that flavor to this flavor into a photon. That's what, when they talk about changing flavors, that's what that's all about. Check this out. This is extraordinary. This is the Venturi, and it's tuned so that some black and mostly white goes through. And here's all the black that came through, which is not a ton of it, but enough that it's pushing the white ahead of it. All right, when it pushes the white and the white has to concuss with something, it glows. That's just the nature of fields pushing against another field. It's called the Casimir effect. And you see how wide these fields are and how close these are? These are called Whistler waves, and they're in the audible range. And these are above audible into the light frequency range. And we can only see in this little tiny bit. But there's a whole batch of frequencies, and all frequencies is the spin. How fast is it spinning? All right? It could spin this slow, which is very slow, or there, or here, 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 or here. And what would that do? It would create all the colors of the rainbow. It's just like CERN shows. Look. These are all the different spin rates. That's not me. That's from Higgs boson from ATLAS. All right, these are all the different colors. And that's because they're different energy levels. Now, they actually, I believe they have it backwards. The blue is in the center. Coming out, you have red at the very outside. That's my take on the atomic model, which is right there. All right, so they had the blue on the outside. The blue is not on the outside. The blue is on the inside, glued extremely tight to the center core. And that's the only time you get blue light emitted is when you really rattle that core. And then you get it out of there. But you wouldn't have it on the outside like this. Blue sits right in there. And when it explodes, the blue goes off, never comes back. The red does stay down and around here, yes. But the blue, well, maybe they got it sort of right. Yes, CERN, I'll give you a pass on this one. No, ATLAS, I'm sorry. Okay, my outstanding friends, I was just getting ready to do this video on these nodules, these concretions that they're mining on the ocean floors. And I am starting to talk about chemistry and the, atomic materials that make up these things that they're finding. And so here I am, I'm going on about it, and all of a sudden, what pops up here, watch. I'm talking about how this is, I understand what's going on here, and nobody else does, literally nobody. So I'm going through all of this, and I'm going to do the video on all of this in great detail, and then that pops up. Well, what is that? Here's all of a sudden I decide, well, I'm going to comment on this, because they come up in here and they say, well, here it is, faster than the speed of light. Information, they're talking about spooky action at a distance at the Large Hadron Collider. So all of a sudden, because this is my realm too, I do both of these things pretty deep. So I decide I'm going to comment.
Light, no problem, done it, no problem whatsoever.
All right, so I figured, well, I'll just keep going, but I couldn't help myself. So we're going to go into light on this one, but the next video will be all about this stuff, and this is an extreme mind blower, as is this. This I've been talking about for years, and now they have literally confirmed exactly what I said about entanglement. All right, you saw that just popped up on the screen. I do research in this area too, and I have found lights going much faster than the speed of light, and I've also found the particles they're going to be talking about here. It's faster than the speed of light. Spooky action at a distance, and this is at CERN. Now listen to this. Here's what it says. An experiment by a group of physicists led by University of Rochester physics professor Regina Demina has produced a significant result related to quantum entanglement, an effect that Albert Einstein called spooky action at a distance. Well, what is quantum entanglement? They're talking about all the time. Entanglement concerns the coordinated behavior of minuscule particles. These are the muons and the electron neutrinos that have interacted but then moved apart. Well, let's see if we can see that happen. The minuscule particles are particles of light. They are the muons and the electron neutrinos. And this is a big breakthrough for physics. This just came out minutes ago, just minutes ago. All right, you see this right here? This is a Dirac neutrino. Neutrinos are the smallest particles that exist. And this is true. There's a white side and a black side. And here's what they look like when they are in light form. All right, you don't see the particle yet, but light, that particle that I just showed you, there's back-to-back particles here, which makes a photon. And it's coming through the air, and it has a field surrounding that little bitty tiny particle. But the field is huge, so it has to plow through everybody else's field. That's why you see all these little bright spots. Those are fields pumping up as this pushes them out of the way. So field to field causes energy and causes glow. Anytime you impact something, you get glow. This is impacting their fields, you get glow. So faster than light, no problem whatsoever. This is light. That's from a red pulsed laser. This is light. And it's the smallest particles that exist, the black one and the glowy one. The black one and the glowy. This is from Fermilab. This is their pictures right here. And they found the same particles we did, the smallest particles that exist, which is from light. Now, can we make them go faster? Yes, I just showed you light being a wave sort of going through, pushing. This is now accelerating to go through a Venturi. Simple as that. And when it did, I told you, whenever there's an impact, there's a glow. It starts impacting against itself because it's pushing back. That's what causes neutrinos, different flavors of neutrinos, is the pushback as they stack up, getting ready to impact. And that's the different flavors of neutrinos. This is very simple stuff, very simple. Light, bip, 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 acceleration, zip, bam, it hits there. The tuned Venturi is so small, only the white can get through, because it can get small and big. The black one can't get small. This is it. This is one size fits all. So when we went through the Venturi, we created fission right here, and we created fusion right there. I couldn't help myself to show this, but let's get back to what I was really talking about, is these spheres, they're mining off of the ocean floor. I'm going to show you all the different styles there are. There's a zillion of them, and some of them have these heavy metals. Now, I'm not exactly sure which ones they are, but I think we could probably figure it out. I know it seems I'm going off course here, but I just can't help myself. This is where the dark matter collects, and then you have all your electrons on the outside. So we've never seen the dark matter because these bounce back at you. This is dipole electron flood theory, and here's the only two particles that make up anything. These are the particles that make up the nucleus. Here they are right here. Each one of these balls has a black and a white side to it, just like a bar magnet has, and it's that simple. And I showed them to you. I probably already have, or I will. And you add two of these together, like this, just two of these, back to back. That right there is light. There are two dipoles. So let's look at that in actuality. This is what light is right here, two of these dipoles, back to back. So they both have a positive and a negative. And back to back, just like two bar magnets. You don't have two whites up next to each other and two blacks down here. No. You have the black and the white attached, and the black and the white attached, the black and the white, the black and the white. These are at angles, and the blacks are at every single one of them. 100%. And this is the only thing. These two make up everything there is. Just these two together, without the other two, is electricity. When you have four together, or two together, that's light. It bounces because it has a big field surrounding all of it. The other one just has one field around it, and it wants to add to something or move into something as heat. It wants to join with something because of its single field. With the double field, it bounces like a basketball. And going through the Venturi, though, is a whole different story. Going through the Venturi, it's so tight that the black just simply can't get through. It just can't get through. Only the white can get through. That's exactly what they wanted to do, and they did, or they don't realize what they did, but they did this. They created muon neutrinos and electron showers, just like we did, only we did it for almost nothing. And now they're starting to take into account just exactly what I've been doing. All right, the spooky action, and here's what they're saying right here. Researchers have confirmed that quantum entanglement, which is these two particles, the black and the white, persists between top quarks. There is no quarks. The heaviest known fundamental particles are top quarks. No, top quarks are just chunks of matter. Everything is made of the particles that I just showed you. That's it. If you want to take a top quark, throw one of these in there. That may be a top quark, but it's made out of just nothing more than these in different configurations. All right. You know, the reason I jumped on this thing so hard is Fermilab and CERN both had found these particles, the black one and the fuzzy, the black one with the fuzzy edge around it, and then the other particle in red. You can see the red easy. The green and, well, here, let me show you something. The blue is just too fast. The green is very fast too. This is the red coming in real slow, and this is the green coming through the same Venturi at the same time and just pushes the red out of the way. You see this? It's got so much energy on the green, it pushes it out, and then it reconcusses way back out here. And the blue is much more intense than that. It's way more powerful than the green. Now, I don't know whether they're actually going faster or they are just a faster spin, because there is a faster spin. There's no question about that. How are they going actually faster? I don't know. because normally when they measure the speed of light, it's white light, which is all the light together. So they're just taking maybe an average, I don't know. But I'm going to tell you one thing right now, there's absolutely no question whatsoever. You can speed up light, you can slow it down. Here's light just getting ready to accelerate. You wouldn't even see this unless it was just getting ready to accelerate. That's why it's getting real glowy. And then you can see that the light is just rocket shipping ahead. That's absolutely exceeding the speed that it started at, which is acceleration, which is faster than the speed of light before it accelerated. There's no question. And it's split and divided, no question. That's fission, that's fusion, no question. That's why I'm so upset about, well, I am upset, because I presented this to Fermilab, to CERN, to the University of Geneva, to all of them. Every JPL, Lawrence Livermore, everywhere, and not a single one would even comment on it. Well, I did get through with Fermilab on a number of times, and it was just nothing but, dismissing me and being kind of nasty. So this has been sitting around for almost 10 years. This goes back to 2013. They knew about these, and I contacted Don Lincoln, the guy that wrote this. And this is where it turned into a kind of a nasty thing between Don and I. He wrote all these different articles. Standard model, most successful. No, it isn't. Doesn't work at all. Quantum foam, he was right about that. Empty space isn't empty. It's saturated with particles. Yes, Don, you were right. Dirac neutrino, yes, they are. The most mysterious particle in a standard model. No, it isn't. Okay, before we get started with what CERN is claiming, originally they talked about entangled photons. Well, the photons are in amongst themselves, but they specifically are not entangled to each other necessarily. They are entangled within themselves. Photons are these little four particles, but they are entangled within themselves. They aren't entangled within each other, I don't believe. But they do come out like this, that's correct. They're saying through a crystal. Well, we put it through a Venturi, which was better. And why would the Venturi be better? There's no obstruction. There's no crystal for us. We have a Venturi, which is just a funnel. And the light has to crush all of its fields, which are big fields, through that little tiny slit. And the black can't get through. The black bounces back, and the white comes through. And we see a whole blast of white. Now, I'm not sure what they're talking about here, whether they're actually seeing the full photons, and I imagine they are. And I don't know if they can actually see them. We can. Okay, this is from the work I did with Rod Warren, and using strictly a cell phone, the Samsung Galaxy S3, and in this particular case, the red ones were done with this exact laser here, the Bosch GLM15, through literally nails, and like 2 or 3 nails side by side, very close to each other, and hitting the light in between them, and they created this. This is basically what I first saw from Rod Warren. Rod is the one that came up with this just totally accidentally. He was trying to do a double slit experiment. And these are the first pictures I saw. And I could see light, it was accelerating. There's no question about it. This one here is just the light pulsing through, because this goes bip, 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 and shoots pulses. Now, the other ones, the red and the blue, I mean the green and the blue, I don't think they pulse, but I'll show you them, you can see them. They might pulse, I'm not sure. But this particular red one, I could see it was exciting the atmosphere in front of it, the fields, and here it was accelerating. And here coming out of the Venturi this direction is at us, is the Higgs fields, just exactly what they show at CERN. And we could actually see the particles. Here they are. I have a better shots of this. And then the blue comes in and slows down. Anyway, when I saw these, that was it. And Rod worked with me fabulously. He's gone sort of dark on this, but all tribute goes to Rod. Because I've got the same things. I did the same stuff here, but I couldn't do it. He must have spent thousands, literally. I mean, it had to be thousands of hours doing this. I worked with him for a number of years, and he never got anything out of it. And finally, it was just sort of, you know, you can only take so much of something like this. And but it proves my electron flood theory, and he's the one that did this, and without this I wouldn't be able to prove it. But I can show now light accelerates. That's what Rod showed, and we can see the Higgs fields, all the things that they're seeing at CERN. But we started with the particles that were smaller than protons. Protons are big balls like this, and when they smash them, all they're actually doing is smashing balls of particles like this, which are all dipoles. So when they smash theirs, they get this. All that stuff. We started with this stuff here. The little bits and pieces, the tiniest bits they can see. We started with that. Like, that's a photon. And they see photons. They just don't know what they know, I don't know if they know they're photons or not. I have no idea. But they also see these X particles with big chunks like this. So they're going to see huge chunks. They're going to see little tiny chunks. They're going to see photons. They're going to see different types of neutrinos. Yup. Okay, let's pick this thing apart. They're talking about faster than the speed of light. They think they can transfer information. I don't know about that. But spooky action at a distance at the Large Hadron Collider. Well, what is spooky action at a distance, and what are they talking about? Spooky what? And it's all about quantum entanglement. Now, this is a breakthrough in particle physics. Quantum entanglement has been observed between stable particles such as photons or electrons. All right, so they've seen quantum entanglement. All right, now I've never seen them show it, but I can show you it. Now, Domenia and her group broke new ground, and they found for the first time entanglement to persist between unstable top quarks. Now let's remember top quarks, which we're going to look at in a second, and their antimatter partners. Top quarks and their antimatter partners. So they interact at distances farther than what can be covered by information transfer at the speed of light. So in other words, they know it's going faster than the speed of light. So they think maybe they can transfer information. Specifically, the researchers observed spin correlation between the particles. What it is, I'll show you exactly what it is. And all it is putting them through a Venturi. Hence, the particles demonstrated what Einstein described as spooky action at a distance. Let me describe it. All right, we're going to be coming back to all of these in a minute, but they're talking about entangled particles. They're not just one little particle entangled. There's a whole ton of them, and yes, they are entangled. I agree with that. All of these things I will show you and explain to you after I explain what they claim they have discovered. All right, this big announcement is because they say they have discovered this entanglement in top quarks. All right, so here's what they found, confirming the quantum entanglement between the heaviest fundamental particles, which are the top quarks, has opened up a new avenue to explore the quantum nature of our world at energies far beyond what is accessible. So these are energies far beyond. If we can find out the entanglement of the top quark. All right, remember this. I've been talking about a possibility of getting possibly free energy. It says confirming the quantum entanglement between the heaviest fundamental particles, which are the top quarks, has opened up a new avenue to explore the quantum nature of our world at energies far beyond what is accessible. These are high energy particles. Okay, this is a gigantic discovery. So we need to talk about what is a top quark. It's also referred to as the truth quark. Well, let's see about that. It's the most massive of all observed elementary particles. Those are the smallest particles that exist, elementary. It derives its mass from its coupling to the Higgs boson. It's coupling to the Higgs boson. Let's think about the Higgs boson in a second. This coupling is very close to unity. In the standard model of particle physics, it is the largest, strongest coupling at the scale of weak interactions and above. It is the strong nuclear force. The top quark was discovered by experiments at Fermilab. Well, I have some experiments that I'd like to have Fermilab look at, because I believe we have found the truth quark. Let's see if there's any truth in it. All right, so let's start off with some ground rules. Elementary particles are subatomic. They're smaller than atoms, and it's not composed of other particles. They cannot get any smaller. All right, and that's the standard model. Says there's these muon neutrino and electron neutrino, which create a fermion, Dirac neutrino, black and white. And I agree with that. All right, so that's elementary particles. Then we get down to the Higgs bosons. Now, they call that the God particle. They actually did call it for a while. And I don't think they understand it. I think they have it backwards. And I'll try to explain that. You see, this is just backwards. They claim that the Higgs particle is an elementary particle. It's one of the fields in particle physics. In the standard model, the Higgs is a massive scalar boson, zero spin, parity, no electric charge, no color charge, and it couples to mass. It is also very unstable. This is what's just not right. Decaying into other particles almost immediately upon generation. No, other particles that are unstable come back and come together. AI-based blood test. All right, here's why CERN and Fermilab are wrong. These do not decay instantly, these Higgs fields. They're seeing huge fields of these circular fields. They're not seeing the single particle fields. These do collapse, yes, but the single particle fields do not. Totally different situation. Now, don't forget, the Higgs field that I'm showing you, these big round fields, they say they're very unstable and they decay into other particles almost immediately. No, the other particles come together to make the Higgs field. The Higgs field does not decay. All right, we got to make sure that we understand each other here. This top quark is the most massive of all observed elementary particles. The only ones really that have much mass are the black ones. So all I can say is all the black ones are the same size. They're the same ball. It's like the same bowling ball. They all weigh 10 pounds. Well, why would one be more massive than the other? It's because it's going with more velocity or more spin. And I can show you that. And I believe blue is what they're talking about for the top quark. All right, listen to this. Top quarks, each as heavy as an atom of gold, can only be produced at colliders, such as LHC, and thus are unlikely to be used to build a quantum computer. But studies like those conducted by Domenia and her group can shed light on how long entanglement persists, whether it is passed on to the other particles, which are the daughters of the decaying products, and what, if anything, ultimately breaks the entanglement. Well, let's talk about that. When they say top quarks, each as heavy as an atom of gold. Well, what is actually a quark made out of? All right, you see this? This is a true statement. They say top quarks, which they are seeing, are each as heavy as an atom of gold, can only be produced at colliders. Well, why? It only can be produced at colliders such as the LHC, and thus are unlikely to be used to build a quantum computer. I want to talk about how could a quark be heavier than an atom of gold. Gold is like a huge thing. It's way up here. All right, one of these quarks is smaller than a proton, because they're smashing protons together. So here, let me show you something. All right, we got a lot to go over, but this is what they do at CERN and Fermilab. They take protons and neutrons and smash them together, and they get all this debris. Now, so they're only starting with a proton and one neutron. When you get up to gold, you got 197 particles of these. You know, some of them are neutrons, some of them are protons, 197. Now, how could they be heavier, the particles given off, than gold, which is 197 of these two particles? How do you gain that much mass? Where'd the mass come from? Well, I could tell you where it came from. It came from a collision, an explosion, and because they're using big chunks. Now, it's still a lot of mass, but it's because that thing is going out so hard when it hits something. That mass is concussion. That's all it is. Mass just sitting around really has little mass except towards gravity. Mass out in space there's no weight whatsoever. But when it hits something, there's a lot of weight. All right, that's what they're picking up on, is this explosion when they hit something. Now, we used light, so we were down in these particles, and we still got the same stuff, but we're never going to get anything like they're talking about, particles like heavier than gold, because that'll kill you. All right, I want to point something out. I know this is extremely dangerous what they're doing, because they're working with big, heavy particles which are parts of photons, protons and neutrons. And so they're getting chunks like this coming off. All right, so they're going to be heavier than an atom of gold when it hits something at 1,000,000 miles an hour. I would not want to be close to this when they're doing, and I know they have to wear all kinds of radiation protection, and they can only stay in there for certain amounts of times. So they're working with radioactive particles. When you work with light, you only get the smallest particles from light, which is the muon, electron, neutrino, and they instantly come back together, which makes the Higgs. So it's just backwards. They think the Higgs explodes instantly and sends off these two little particles. It's just the other way around. The two little particles come together to make the Higgs. And I can show that and prove it. All right, here's what they're doing. They're hitting basically two of these big balls of particles. There's like at least 1,823 or so in each one of these balls. And when they hit together, they send off all of that debris, yes. And it's all different colored flavors of energies, because you might hit just off an edge, you might hit this way. Every now and then you hit perfectly head on and you get these exquisite Higgs fields. Now, they collapse instantaneously because they're just huge amounts of particles that will recombine. We did it with light, so we started with these particles that are the tiniest particles that exist, which is light, and then we split those. All right, you see this? This is dipole electron flood theory. All that exists is the white electron and the dark muon. The muons go right to the center because they don't repel each other. The white ones, they repel each other like crazy, and they want nothing more than their whole world just to be attracted to that dark muon. That's what gives electricity its power. Now, those two particles together make this. Now, I showed a white one and a black one. Well, why am I showing red, blue, and green here? Here's the reason. The black, like I said, doesn't matter. It will go right on top of itself and just couldn't care less. But the white wants nothing more than to be attracted to it. So a whole bunch of white ones swarm in on it. And there's a certain number that it will accept around it, and then the rest, they'll say, no, we got enough, get out of here, get out of here. That's the stability zone. That's the the periodic table. Each one of these is a number of these particles here. All right, it's not like hydrogen is not one of these and it's something that's so tiny you couldn't ever imagine it as an electron. No. The proton is made out of dipoles. That's all that exists. It's dipole electron flow theory. And this is going to be like 1825, this is going to be like 7,300 or something. Up in here, I think gold or somewhere up in here, I forget, maybe it was uranium I did, was like 310,000 particles make it instead of like 97 or something. I forget what it was. But for every neutron, multiply 1824, and every proton, multiply 1823. And between those two, as you go up, you've got protons and neutrons, just multiply them. It gets big quick. So this is the true model. Now, why the blue, why the green, why the red? Well, the blue is so tightly attached because it's right on top of the black. It's hugging right up there, tight, tight, tight. They're just held together, just really glued together solidly. So if that is going to take off, you're going to really need some energy. And then, pew, it goes, never comes back. The green is pretty tight too. That's a strong attachment as well. So a lot of that will go pretty much. There's yellows and greens and orange, there's different colors in there depending upon how hard it got hit, how fast it's spinning away. It's not just red, blue, and green, but those are the primary colors, I think, that come out of that's what you see from these crystals. Anyway, the red is on the outside, they're sort of just hanging around out there. That's why red is not a real strong attachment. And as a matter of fact, here's what Fermilab shows right here. Here it is. So what are we seeing? We're seeing the explosion here is the particles smashing together, big balls of them. Boom! And everything goes. Well, the ones that were really stuck onto the black ball, which would have been in the center, here's exactly what it would be like. Just like this. All right, now you got two of these. Bam! And all of these white particles push each other like crazy. The black just goes away. They never even see it because the black is dark matter. They don't even see it. And the white ones go flying. Now, the ones that were real close to the black go blue and they go just take off forever. They see white ones too, yes. Green and yellow, that usually goes. And then you start to get to the red, and the red, it wasn't attached so tightly that it can go forever. So the red is the particle that is going to be, the one that doesn't really escape as much as the other ones. And red, you can work with red and actually watch red progress. Here it is right here. All right, it's going through the air. And here it is being accelerated like a rocket ship. All right, and there's the actual particle, which is actually just this right here. Is two dipoles together. That's the photon. And it sees this Venturi and it has to accelerate. And by here, the field is coming back so strong that it thinks it hit the wall. So it starts to glow like it hit something. Same thing with these. Those particles are in the air. You're never going to see those. Those are particles of light. You never see them. You never see them. And you never see this one either. Why, Roger, do you see that one? Well, the reason is it's directly in line with the Venturi, and that field itself is being sucked forward, not being pushed back at. Here it's being pushed back at. Here it's being sucked forward. All right, a quark is nothing more than a big chunk of a proton. And they say there's several quarks inside of a proton. So they're using bigger balls of matter instead of... All right, so they're working with top quarks. Well, as we know, the top quarks are chunks. Quarks are like several of them within a proton. There's not several of them within a proton. There's all of these particles within a proton. So they're seeing like chunks. And they might become stable at three little particles in there, whatever it is. There might be a little bit of symmetry in there. I'm not saying there isn't, but each one of these, the entire mass is made out of 1,823 dipoles. Just go with that. And a neutron is 1824. And they understand they can get rid of one electron, they say, and go down to 18 and become a proton from a neutron. They add one, it comes back up to a neutron. It's just amazing. I can't understand this. So I'm working with the most elementary particles there are, which are light. Now don't forget now, my dipole electron flood theory says there's 1,823 dipoles in here. We work with light, so we're down in this range. They're talking about quarks, an top quark. All right, and what is a quark? Quark structure of the proton. There are two up quarks in it and one down quark. That's just not correct at all. The strong force is mediated by gluons, and they say there's gluons in between here. The strong force has three types of charges: red, green, and blue. Note that the choice of green for the down quark is arbitrary. The color charge, blah, blah, blah. Well, I'm saying there's 1,823 particles. I don't care how you cut it. And they're all made of the same particles, which are these two right here. That's it. That's it. Every one of these little dipole particles is a dipole which has a black and a white, a magnetic charge to it. So they could actually strip out in chains like that. All right, let me show you something. You see that chain? Here's another chain. These are polarized. If I come to this thing here, this is going to want to attract. If I come to that with this side, it won't go together. See it? There's nothing I can do to make that get together. But if it goes to the right polarity, it's just done. And there's going to be a certain number, for some reason, I don't know what it is, whether they wrap around themselves or whatnot, but there's going to be a certain number that makes it stable. And it appears to be, of these, each one of these dipoles, there appears to be 1823 in a proton, which is the odd number because it's charged. 1823 means it's not even. So it either wants one more to become stable even, or it wants to give one up to become stable and share with somebody. That's what chemistry is all about. Now, what happens to the black is it pushes right into the center. I probably made this point about 5 times already, but people don't seem to catch on easily. That's where the dark matter is. We have never seen it. It's in front of your face. It's everywhere here. Dark matter is in everything that you see, but it's behind everything you see, and it does not radiate, it does not absorb, it doesn't reflect, it doesn't emit. So you could shine light onto that dark matter, you would never see it. The only way we can see it is because we have it on top of the white, obstructing the white. You see here? There's dark particles on top of the white. Let me get a better shot. Well, hold on a second. All right, I'm sorry, I missed this right here. This is at the Venturi. The only reason we see these black balls is because they're on top of the white. They're all exactly the same size. They're all the same size. One size fits all, and I can show you on the green, the same thing. But the white is the only part that can get through this very tight restriction here. So the black backs off and the white comes through as a shower, which is exactly what they say. This is what exactly they're looking for. The muon neutrino, which was the black ball, and the electron neutrino attached together makes a Dirac neutrino. Di means two. And the two of them separate when they go through heavy water, and the black goes on its way, and the white showers off into craziness from electron showers. Very, very, very high power energy, extremely high power energy. And I think it might be able to be used. All right, listen to this now. Top quarks, each as heavy as an atom of gold, can only be produced by these colliders because they're chunks of smashed particles. Thus, are unlikely to be used for quantum computers. Now, the studies like those conducted by Domenia and her group can shed light on how long entanglement persists. How long does that particle stay entangled? I'm going to show you how long they do, and whether it is passed on to the particle's daughters or the decay products. Those are the isotopes. And what, if anything, ultimately breaks the entanglement? Well, I can explain all of those things right now. Okay, I got called away a couple times. I'm not sure where I was, but I'm just going to try to show everything to make it make sense. These are the two entangled particles. These are the entangled particles they're talking about. Now, normally they see in the photons they have seen, which are these. These are entangled. But now they're seeing not only photons, they're seeing a chunk like this come flying off because of this heavy collider. They can break these things into balls. So they're seeing that, and they're seeing it go, and how long does that ball stay together? Well, it stays together according to how long it interacts with all these other particles. And it depends on what they're seeing. Are they seeing actual light particles, or are they seeing both the black and the white? I think they're seeing like what they call an X particle. Let me show you what they do. And this is what I'm not sure about. Are they just seeing this, which means it's one of these, which is a part of one of these, a big part? And then how long does it take before that falls apart and joins back into an atomic mass, or decays into just electrons? Because that's what they'll do. These are in the electron state. That's a photon. These are, the electrons. They don't see the dark matter. But every one of these is going to have a dark matter attached to it, more than likely, or it will very quickly. They could be seeing these. Is it this they're seeing that is heavier than an atom of gold? Is it one of these? And they call it a quark? Because it is. They said it's a top quark, and there's only supposed to be 3. So it must be a third of one of these. And for some reason they say it's stable. A quark is more stable. It's a unit of stability. I don't know. They don't know what's going on, because you got to understand dipole electron flood theory. It ain't bragging if it's true, and it's true. Okay, so they're looking for certain characteristics in this stuff, and specifically the researchers observe spin correlation between the particles. Now, they do spin together, and they spin away from each other because of the field separating them out, and I'll show you that. It says, hence, the particles demonstrate Einstein described as spooky action at a distance. Let's take a look at that. Remember, they're talking specifically, they observe spin correlation. Something's going on between this spin and that spin between the particles. Let's see if we can figure that out. Okay, this is their model of the atomic model, and they think all these things are separate little bits and pieces, which they're not. The only thing that exists is the W and Z boson, which are always attached together, and the Higgs boson is nothing more than the two of them coming back together, and you see them. And that's what the only time they see the Higgs boson is when the two of them comes back together, as I showed you. Now, when they come back together, they are gluons. 2 gluons make a photon. That is it. That's it. The rest is just manifestations of these two black and white particles. And the Higgs is just nothing more than when they break them apart and they see them coming back together, they say, oh, they just broke apart. No, they just came back together. Okay, this is not just a mind exercise. If we could really do what I'm talking about, and I don't know if we can or not, I'm just theorizing. But I can tell you what, I could see that light backing off of here, the black and the white coming through. And if we could harvest that white, the white is exactly what you need to make your batteries charge. We did nothing whatsoever other than force it to come through these Venturis. And you could have a whole slew of them and lasers running them, and you could harvest up a whole batch of this white. And that's all you want. It has no weight whatsoever. You charge a car up and it weighs 4,000 pounds when it has no charge at all, and you drive all day long, it still weighs 4,000 pounds. Charged or uncharged, doesn't matter. The charge part has no specific weight to it. It just has a lot of energy, and I cannot account for that. All I can think of is there is some minuscule amount of weight, which I believe there is, but it's so minuscule you almost can't measure it. And it almost like forms soap bubbles or that type of thing. Real thin fields. They're fields. Whether they have some, I can't think of anything that could create a field and be nothing. It just doesn't make sense to me. But there is just almost no weight whatsoever. And I'll show you, I can confirm that in the atomic bomb blast. But if we could harvest this huge amount of energy, this could be put into something like this. You could walk around with that. Plug anything you want into it, any voltage, any cycles, USB, AC, DC, seal it up so that it couldn't be damaged. And you could have probably enough in something like this. You might even be able to drive a car. I have no idea. I have no idea how much energy you could get out of that with the right system of the right kind of laser, the right type of Venturi, because none of this has been worked on yet. It's just we just experimenting. But you can see that it accelerates and the white separates from the black. The white is where all the energy is, which I will show you right now. All right, this is atomic bomb blast. And they had a truck here delivering the stuff. They took the truck out of here. I have all these people say, oh, it's fake. The truck is missing. No, the truck was just driven away. And there is a hardened enclosure that held the camera equipment facing away from the bomb blast so they could see everything and it would not get knocked over. So get past this conspiracy nonsense. This is what happened. Now, this is running extremely slow motion. And you'll see. The white is the outside is the white. All right, inside the white is the black. All right, so when the bomb goes off, the white gets pushed off first, and there it is right there. You see what's happening? Just nothing but whiteness, and now nothing but smoke. It's not even going that way. The poles are smoking, the wires are smoking. Everything that is combustible is combusting. All right, these metal tanks are not combusting, they're metal. And this is on the side, so it's not being hit head on like this is. Now watch the roof. Watch how, like I say, I'm running it slow. It's just smoking, And all of this is starting to glow and just smolder and smoke. Now boom, there it goes. So what did we just see? We saw the white particles smoking the house up. All right, that's what we saw. We saw that just smoke. No movement of anything. Nothing is moving, just smoking. So that's just the white. Now comes the black. Boom. That's the separation between the core and the surrounding particles. Okay, I showed you the core is the dark matter, and that's got all the weight. All this stuff doesn't weigh anything, but it's energy. That's when the atomic bomb goes off. They crunch it in like this, and when it comes back out, all of these particles go first. Then the black follows them. That's why the house just burnt up, and then the black hit. Just like this picture right here. that Rod did. Look at this. This is it right here. Let's say the house was right here. Boom, it goes off. Everything comes out, and all of a sudden the house starts to burn up, burn up, burn up, burn up, burn up. Then the black hits, there goes the house. That's what happened. All right, this is really nonsense. Einstein was not right about virtually anything. I'm sorry, Albert, you just didn't make it, my friend. His challenge to quantum mechanics. He's saying that in quantum mechanics, two particles are entangled if we know the state of one of them when measuring the other. So how do we know the state of one of them when we're measuring the other? How do we know that? If you can't find that other particle that was just held onto this particle. This one goes here, and they were entangled. They just split. They just went crazy. It says this is true even if the two initially entangled particles are placed very far away from each other before the measurement, whatever that means. This is what Einstein referred to as spooky action at a distance. Well, he doesn't understand that light accelerates. Light's a particle. Dipole electron flood theory, none of that stuff. I show you nothing he said was right. Explain this to me. Explain how that can be accelerating like that. In the atmosphere, we're not even in a vacuum. And they had to base everything in space on Einstein's law that says the speed of light is constant, can't slow down, can't speed up. That's just absolute nonsense. That is speeding up. Nobody can say that as not speeding up. It went from this to what I just showed you. And if that's not speeding up, that's just nonsense to say it isn't. And the same thing with the blue. The blue is slowing down. It would be nonsense to say it's not. That's tighter spin, and that's a looser spin. By the time it gets out here, we can see both particles. The blue is so fast we can't work with blue. And we can also see the red and the green interact together. And the green actually pushes the red out of the way. And then instead of the red spinning like this, according to the polarity of the Earth, it's pushing that, and it's barrel rolling. Can you see that? That doesn't happen. That's a barrel roll. They normally polarize to the Earth. It's upspin and downspin. And it just depends on where the black is, up or down. But that's a barrel roll. That does not happen. Now, I want you to know, this is not new to me. I was in the Army in 1968. I went in the Army, and I serviced Nike Hercules missile sites. It was better than being in Vietnam. Now, when I first got out of the Army, I went into physics. And this paper is from my interaction with all right, just to show you, this is not new to me. In 1970, my paper, which I wrote saying the Rutherford's atom was wrong, which means the Bohr model is wrong, nothing is right, the transfer of energy is from light to atomic vapor. Well, what is atomic vapor? There it is right there. It's those little tiny particles, those dipoles. And everything was dipoles. Dipole moments all over the place. Dipoles. I had something else down here, something about, there's only two types of dipole interactions. These papers go back a very long time. And this was my final paper about it. Making a very, very strong case. And, you have to take into account the repulsive forces between the nuclei, repulsive forces between electrons, attractive forces between the nucleus, yada, 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 yada. And everything is made out of dipoles, which is dipole electron flood theory, which is the best working model of the subatomic particles. And it means that we need to change the periodic chart to adjust for these different quantities. I don't think there's a whole lot of change to be made because they seem to be stable at different quantities. So we maybe just have to change the atomic numbers and stuff. A couple little things here and there. But I'll tell you, one of these little charts, this is the best thing you can ever have. You can look anything up. On the back, they got everything you want. Fundamental physics, constants, all constants. That's the problem. All these constants, you've got to use these to do your formulas. I get a lot of people say, oh, you don't have any mathematics. I don't need the mathematics. I'm showing you the particles. Who cares about the mathematics? It appears that there's 1,823 dipoles in a proton, 1824 in a neutron. I arrived at that because of Millikan's oil drop experiment, which calculated out the weight of an electron to be 0.000085485 something. And if you divided 1, which is the atomic mass of a proton, by that 0.0005854, whatever it is, you end up with 1823, which is what a proton weighs. That's what I got. But I'll tell you, these things, listen to this. This will freak you out. I'm looking for coefficient of friction. I can't remember what it was for, but, you know, steel on steel, how much friction do you have? Copper on steel, rubber on concrete, wood on wood, glass on glass. Listen to this. And it keeps getting less and less and less friction. And you get down to ice on ice is 0.1 and 0.03. Teflon on Teflon is 0.04 and 0.04. And then you get down, listen to this, human synovial joint fluids, 0.01 is the least of anything, way far the least of anything, and 0.003 way by far the least of anything in kinetic and static energy both. That's what's in your joints. That's why you just got to move freely. This stuff blows my mind, the little things you can figure out from just on this little chart like this. And then you get another one that was, I got it around, this one here is all about the visible spectrum and how long these frequencies are, what they relate to, bacterias, and, you know, up here you got nothing more than the really heavy duty particles. Anyway, this is, I love this stuff. You should love this stuff too. It's fabulous. It's wonderful when you understand something. It's depressing when you present it to people that should take an interest in it, and they don't want to know anything about it because it disrupts their apple cart, and that apple cart is full of apples that are actually money. And it's about funding, it's about all that stuff. Once you're in this academic realm, it's all about funding. I take courses all the time, and I use Coursera. Free, it's free. And so I take them everywhere. I took one at the University of Geneva for particle physics, genomics at Johns Hopkins. I took all kinds of them everywhere. And one of them that I just recently took, I can't remember where it was, the first class was how to apply for funding, how to apply for grant money. I'm not kidding you. Right off the bat. I was shocked, but I'm really not shocked because what's going on is shocking.